Okay, so if you have others interested in watching through YouTube, you can use this link instead. I would like to share this link. Stream on YouTube here. All right. Okay, so I guess we can start right now. It's good to have you here again for another session of DevMeets. And we had a wonderful session the last time where we saw several, opinions on some software patterns, including modeling real life software and among other things. And today we'll be starting a series. This is the beginning of a series. We'll be having about 4 to 5 sessions in this series, where we'll be doing sessions on system design. The idea is to look at really challenging systems, try to model them, see how they work, see how they fit in, see how they usually work in real life. And I'll be having different developers in different sessions like this to handle this design. And by the way, they do not know what they will be designing. They have no idea. I have not informed them. So right here on this call, you and the developer will be made aware of what they'll be designing at the same time, and they would be sharing their screen. Today we'll be having Bofade. He'll be sharing his screen and design something before us. He'll be using a drawing tool. They could use Escali Draw or whatever tool they think is really beneficial for them. By the way, I did not introduce myself. I am Lord Sarcastic or Ayodeji, and I've been the host. Right, so we'll get started. Bofade, do you want to introduce yourself?
Okay, let me introduce myself. Yeah, good evening, everyone. My name is Bofade Uyerinde. So I think I've had quite an experience in developing. With the years of learning, this around 7 years of learning, and then with 5 years of professional experience, when I mean working experience. So I've been working on real life experience since the last 5 years.
All right, that's beautiful. I've known him for a long time. By the way, he was my classmate back in the university, so we go way back. And I'm so happy to have him here. Right. Okay. Before we go on, I want to drop a few things. Number one is DevMeets has several avenues which you can follow. Right now, you can follow on Twitter, right, or X. I still call it Twitter because it's kind of weird to say the word X. Right, so you can follow it on Twitter. You can follow it on YouTube. I'll drop the respective links there. All I want you to do is simply just click on follow and click on subscribe. Right, it's that easy. Just click on follow, click on subscribe, and I would really appreciate it. It's not my personal channel, right? So yeah, just follow to support what we're doing right now. A few things. Questions will be taken at the end of the session. I will be engaging Bofade in a discussion. I'll be asking him questions, so it's going to be more like a conversation. And at the end, I'll give some time for questions. So this whole session will last for about 30 minutes, and then we'll have time for other people to ask questions and engage in discussion. All right, if you have any questions, please just keep it to the end of the session, and then I'll be taking you on. With that, let's get into the game. And today we'll be designing, drum roll. Today, Bofade will be designing a ride-hailing backend like Uber. So designing something like Uber. Your design is just supposed to incorporate the idea of matching riders with drivers in real time, the pricing logic, availability of that's what your design would basically cover. Again, riders, people that are booking the ride, the drivers themselves, matching them together, availability logic. And if we have time, we'll talk about moving from source to destination. All right. Did you get that?
Yes, I get that.
All right. So With that said, let's get started. So I'd like to ask you, first of all, how would you usually go about designing things like this?
Okay, if I'm given a problem, about to design any system, I use a UML diagram to map out what I'm going to do. So, diagram, but out of those various ones that we have, I only make use of three there. The first one is the use case diagram. A use case diagram is this kind of diagram that depicts an actor and their functions. So an actor simply means that a user that actually system, so divided by rows in the system. So using the rider Uber as a case study, so definitely it's going to be the driver itself, the clients that actually wanted to book a ride. Probably there is another person. It can be the admin. So probably there are three actors in this system in which the three of them perform different function as some kind of function or tasks that are actually grouped together as well, that they perform in common. So that is one. And then secondly, I'm going to design something called a user flow. A user flow is more of like a flow chart, how that actually flow from the top to the end of the whole program. What is the first thing to be done in that system, followed by the next step, followed by the next step until the end of the flow of the system. So that's another part. So the third one I'm going to design is the ERD, is the entity relationship diagram. It's a kind of a diagram that depicts all the entities of the system. What I mean by entity is that a user in the system can be an entity. So that particular entity, I'm going to design them with every other entity and their relationship, the way they relate with one another in the system. So by giving all this theory, I don't need any other UML diagram again. I can be able to start and just after that, I can be able to come up with the technological stack that is actually useful in that particular scenario.
All right, that is beautiful. Thank you very much. So with that said, let's dive into the diagram, to the design. All right, you have the floor. Let's go ahead, share screen, and let's walk through this.
Okay, let's start. So let me share my screen.
All right. Right.
Okay. Can you guys see my screen?
Loading. Yep, I can see your screen. It seems to be showing only one line, right? Just you're sharing your entire screen.
I'm sharing my entire screen.
Maybe you can stop sharing and then reshare again. It's just showing a single. It's not showing completely. Okay.
What about now?
Much better. Much better.
Okay. Now in the system, let's break the system down. What we're actually building is form of like something like an Uber system. And in this system, how does it really start in the system? Now, let's break it down one after the other.
Sorry to cut you short. Please feel free to ask me questions on constraints and, certain decisions where I have not been explicit on.
Okay. No problem. So now let's start. So before I start, I have a question to ask. If this thing, is it exactly like Uber or someone who has not even registered can actually book a ride? Is it possible?
Let's say only registered users. For now, let's assume the authentication aspect has been done. You don't have to design the authentication flow and all of that. Let's assume everyone in this system has been authenticated. Riders have been authenticated as riders, and hailers have been authenticated as drivers.
Okay, so let's just assume that there are already people in the system already. The riders are there, the clients are there, and the admins already there in the system. So just the flow of the booking of the ride, right?
Exactly.
Okay. So now let's start with the use case diagram. Let's start with the use case diagram. So this is the start of the system. We're having the start of the system here. So now we will be having a client wanted to book a ride. So this is the client here. Now, for every time that the client actually logging into the system really needs to ask for permission. So you need to ask for permission. So location permission needed to be required. So location permission in the system. So if that location is being granted, so it is supposed to be another diagram. So now this kind of diagram is actually made for decision making. It's made for decision making. Yeah. So now what happens is that a permission is being requested to access your location. So after that, given your location is going to get, once you have access to it, let's say this is yes. From here, you have access to the location. This is yes. So if no, you will not be able to perform any action here. You won't be able to perform any action because to do that, your location is very required. To book anything, right? Your location is required. So now, if it is yes, the system grabs your location. From the location that you have, then starts looking for that are within. So 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 a lot of riders will be riders. Now, all these riders, they already have their location set up. And the way they are moving, their location is actually changing unless they are in a constant place. On location is actually there. So once your location, your latitude and your longitude will be used to determine the distance between you and the rider. There is a calculation for that. So every rider will be listed and be shown to you. Now, how does the price is being determined? So there are various constraints that determine the prices of all these rider. One of the first things here is the distance. The distance between you and the distance between the rider. Hello?
Yeah, this
Can
is
you guys
not
hear
a,
me?
yeah, I can hear you.
Okay,
Sorry.
okay. So one of the things is that it is the distance from where you are to the location of where you are going. Are we together? So that determines one of the constraints there. And then there are so many constraints that might not be visible to us, the user. Another time is probably the weather condition also determines as well. Weather condition determines the price as well. That's another factor. And then another factor to be considered there to determine the prices is the request. So factors. It is the request. I mean how the request is actually maybe many requests. So if too many people are actually maybe going to a particular place, the price of all those things will definitely be higher. So I will just use them there. We have the distance.
You stop sharing your screen.
Stop sharing. Sorry. Yeah. Is it up now?
Yep.
Okay. So we have the distance here. We have the weather condition. Weather condition. We also have the frequency of requests.
Okay, for the purpose of simplicity, can we consider only distance?
Okay, so let's consider only distance for the sake of simplicity. So now this distance determines. So the distance determines the prices. So there might be a set price for every distance. They just, okay, if it is within 1 kilometer, if it's within 1 kilometer, let's have this particular price. If it's within 2 kilometers, let's have this particular pricing. So those are the factors that determine the pricing. So after getting from there, let's say these are the rider, then we have something called matching here. Matching here. So you make a request. Let me put this one like this. So we have something here, matching. Before a matching can occur, now you send a request to rider. So from here, we're getting a request to the rider. Yeah. Now, if the rider, this is the rider. Sorry. This is the rider. If the rider accepts the request, then we are going to have a match. We are going to have a match. So this is how match occur. Then as time goes on, when your vehicle is moving, they also have a tracking system. In case that you are not actually going to that particular destination, the prices changes as well. So when it matches, then the ride can begin. So this is all the way everything runs on the system. Now, this is the first thing to consider, which is the data flow. It might not really be perfect. So from here, we can actually go to the second diagram, which is the use case diagram in the system. So okay. I think let me use a eraser.
Can you walk through what the use case system would look like?
Okay, now concerning the use case system, it's not something that is actually hard. It is just like drawing like 3 human beings. It is more of like a human being. You are drawing a human being. They have let's say this is the first human being here. This is the second person, and this is the third, and this is the third person here. So all these 3 in the use case diagram, we call them actors. Now we have functions in the system. So these are the functions. These are the functions.
Okay, I would imagine we focus on having to architect how different aspects of the infrastructure would communicate. From the user making a request to the server, and the server making requests to the riders and all of those things. I think that's what we really want to see. So we don't have to see the the use case diagram. I think given that you've given us the data flow, how everything works, we can just jump to that.
Okay, now let's go into the main listing.
Yep.
So now you as a user, you're a user here, wanted to make a request to the server. This is the server here. This is the server here. Yes. And we are having driver here also connected to the server. So when the client here send a request to the server, you send a request to the server. The connection there between the client to the server, we are going to have something like a WebSocket for a real life scenario, because this thing happens instantly. So when you send a request to the server, immediately the rider gets the request. It's an event that happens, and it is more like a server-side event. So when it happens, this server-side event, when it happens, the rider here gets the notification of what really happened. So in between, there is a kind of a technology that is behind the Uber. It is more of like a H-theory. It's H-theory. So this H-theory allows them to match you with the right rider that is on this thing. We can actually go through it later. H-theory design by Uber.
Yeah, I think we can look at that, because
so we can do that later. So it's actually a very complex this thing. So with H-theory, they can be able to use. Okay.
Yeah, I have a question. So you mentioned, first of all, that the user is making a request to the server, making they make a WebSocket connection. At what point is the WebSocket connection initiated? Is it at the point where they request a ride and it is initiated, or the moment they log in?
Okay, it is not actually the moment they log in. Okay. It is at the point where the server is actually sending a signal to the rider. So, but this, I think that WebSocket might not be even perfect. So the best of use is actually a server-side event. It is more of like a notification. More of like a notification. So, more like a notification.
What I mean is the client, right, is making a request to the server. Right now, I can see that the client is making a request to the server. So this request, is it a WebSocket event or the rest?
No. It's actually a normal request. This is not a WebSocket. This is just normal HTTP request, just sent to the server.
Okay, I see.
Yes. So in between here now.
Sorry. Okay. Is there any reason why you decide to make a REST call? I mean, why not initiate the WebSocket connection here?
Okay, I don't think it's actually really necessary to make a WebSocket connection very, very on start with this thing, because if you are going to make a WebSocket connection, it's supposed to be something like maybe something that is going to be immediate, sharply. But if at the point whereby the rider here accepts, then socket connection can happen in that particular place. So they can able to talk freely. So at this point, every driver's geolocation is being stored. So the best way to be able to access this thing is by using a Redis. So when everything is being stored in Redis, so the connection is actually much more faster. So the connection does not actually reach into the database. So from the rider, from the rider,
might have multiple riders in this case. Let's say like 10 riders, right? Well, let's assume we have like 10,000 users in this whole system, right? Let's say 5,000, 10,000 people who can possibly hail for a ride, and 10,000 riders in this case. At this point, who are we sending the server-side events to? Because right now we are making a request to the server, right? And from the server, we are making another request to the rider. Yeah, you mentioned they are going to send a server-side event to the rider. So does that mean there is already an existing connection between the rider and the server? Is that what that means?
Okay. Thank you very much. There is already existing connection within the rider and the server already. And that kind of connection is more of like a WebSocket connection.
Okay, yes, so 10,000 WebSocket connections, right?
Yes. Now, the essence of that connection is that the allocation is being sent and saved via Redis, because it's not something, because a rider now can be on a journey and be moving. So when it is moving, for every second, the request should be sent and be saved. So making such kind of a request to a database for a very long time, it's going to wear out the database. So it is better to put it in an in-memory database like Redis to save their geolocation. Yeah. So now, when the client sends a request to the server, it does not actually come immediately. Pass through the safe location of all the riders here. So before it's sent to the rider, we have so many riders that is going to be shown to the users. That is going to be shown to the users here. So from there, after they now send another one, like, okay, let me accept this one. That is when this event actually happens, this server-side event. That is where the connection between the client, the one booking for the ride, and the rider actually occurs.
Okay, so this means that now I'm trying to like understand the flow, right? Just for the sake of other people too. So now the client sends the request to the server, and what the server does is that the server tries to retrieve the geolocation of all the riders, right, and broadcast it back to the client, isn't it?
Yes.
So now this return, this response from the server back to the client, is it within that same request response cycle where the client made a request? So this means when the client made a request, in that same request response cycle, the server is grabbing all 10,000 geolocation, and sending all 10,000 back to the client as a response. Is that it?
According to what they do, they don't send too many these things, because once we actually need the highest recommendation I've ever seen, it does not pass 5. I don't know whether if there's any company other than Uber do more than maybe 5 recommendations of your riders. So they don't need to go through this thing. They just find the one that is so near to you.
I see. So that means that the client is broadcasting their location alongside their destination to the server. And then the server does some kind of check before returning back to the client, right?
Exactly.
With 10,000 users, how do you think this will scale? What resources the server should the server really have to handle such? Or we can leave that to be negligible right now. Let's assume the server has infinite resources. Okay, so we calculate all that and return that to the client within the same REST call, isn't it?
Yes.
Okay, good. I'm just trying to fill in all these details. You can also help fill in these details to help others understand. All right, go on.
Okay. Now the clients, when they are sending requests, there are things that is contained inside a particular request. One of it is their location, the current location, because location changes every time. So their current location with where they are going, that is what is being sent to the user. So what I showed that particular time, that H3 diagonal, it is what they use in calculate. It is actually an in-house tool that they make a public something so that they can use to calculate the distance. So they will now find the driver that is so near to you. That is what they do. So even though we have millions or thousands of drivers in the system, they don't really need to go through that. They will just something like that hexagonal. It is more like an hexagonal. So they will just draw the line. So within all this line, anybody that is within there will be returned back to you. They will be returned back to you. Since the data is not actually reaching the database, because at times those on the riders has already have their location being saved and being tracked every second and saved into Redis. So they don't really actually go, even though because I've already used Redis before and I know the capability of Redis, the way it is so fast, again database, because if you use Redis compared to a database operation, the margin between the two, because I performed some kind of operation there, on a database level, I'm having like maybe 1 point something seconds for that request to take place. But within Redis, I'm having less than 20 milliseconds. So 20 milliseconds and 1 point something second, that is roughly 20 to 2,000. So I've already slashed the thing almost by 100. So if I'm not mistaken, yes, 20 milliseconds divided by 2 seconds actually like 100 times. So I've already slashed that request. So having a large number of riders in the system does not impact the performance, because it is not going to look through. It is just to check the one that is so near. That is what is going to use. Okay. The way you can be able to do that, there is something in the data structure and algorithm by using the B-tree. So if you're actually looking, using the B-tree, much more faster.
Okay, is there any reason we would use a B tree here? In that we already have Redis that is handling our retrieval or driver location, why should we introduce another data structure? Could you clarify
Okay,
that?
now using the B tree in a situation probably when are you using Redis, so it's actually an overkill. So there is no way for you to be able to do that kind of. But if actually maybe working with database directly, if you are going to do that, maybe you are going to have a database that supported that kind of a thing. And because if you are going to use normal database, you might have a lot of issues. So there is absolutely no reason to have that. But if you are going to go with any database that supported that, you can be able to use that. But regardless of the fact, Redis is still more faster than using normal regular traditional database.
Okay, I guess we can skip that. So yeah, let's talk about the matching process, right?
Okay.
Yeah, go on.
Now concerning the matching process. So after you already sent a request to the server and the server gives you the response back. So what's another, okay, from all these people, which one can I actually go for? Because as of then, there are prices that is being listed here. So on the rider side, I don't really have experience of how that one works because the prices normally varies. Maybe they allow the driver to set their own prices. Maybe the minimum price that they can go. I really don't understand the way the thing works there. But given the distance, using the distance.
Yeah, let's have the assumption that we use the distance to calculate.
Okay, yes. So now, if you are using only distance alone, so their location and the client's location, I mean the one sending for the request, is going to use to determine the prices. So there may be a little variation for all those things there. So after the list, I can just pick one there. Then when I pick one there, something happened there. A request is being sent. So when a request is being sent, that one will stay on the request list. If there is a database table for that, so there is going to be a request. So that request is going to have the information of the sender, then the information of the rider as well. So immediately it accepts it, then it becomes matching. So if it's declined, just like you are sending a friend request, or maybe on Facebook, or maybe you are sending a connect on what is it called? On a LinkedIn. So that is the way the thing works. So once you send and actually accept, that is when it actually takes place. Once it declines, that request is not valid again. So it is being deleted immediately.
All right, so I have a question here, right? So you mentioned that now the server returns the information of, say, 5 closest drivers to the user, yes, alongside their respective price, isn't it?
Yes.
And yeah, and then the user gets to choose. This means we are going towards the direction of the way InDrive works, where you get to choose your price. I mean, and that's all right. So now the user now selects one of these rides that they want to work with, right? Let's say they pick the first one,
yes,
and
yes,
it is being sent to the server as an HTTP call, isn't it?
Yes.
Okay, and when you make that HTTP request to the server broadcasts that event to the rider through server-side event. If I remember correctly, the server and the rider, they have a WebSockets connection. The client, yes, the person requesting, and the server do not have the WebSocket connection, right, or socket IO connection. Let's assume we use that interchangeably. So the rider makes a request, right, and this HTTP request waits until this rider accepts this request. And this means that this HTTP request would remain on for, like, say, let's assume it takes the rider a minute to confirm. We are expecting this request to take a minute to be fulfilled. Don't you think that might be expensive? I mean, why are we going to hang up the server resources making that decision?
Okay, actually, that is an edge case that I did not even think of. Yes, you're actually right here. So that is an edge case. So in that particular scenario, because I've not really waited very, very long time, but in that particular scenario, there in the, maybe this one is not actually maybe in the aspect of a development, but maybe in the coding aspect of it, the system might actually pop up to the user that maybe I use it trying to wait for this particular ride or pass to the right. So in that particular case, I think that could really solve the situation. And since it's just a particular kind of a request, it's just a one time. And once the request is being sent, I don't think there is no any other issue, because it's just a one time event sending. You just send the request there.
How about this?
So it's just only one.
Yeah, there's a small problem there, right? If the person requesting is waiting for the rider to return a response, and that it takes 1 minute. Now this request takes 1 minute to be fulfilled. Now you mentioned that the system would request from the driver, from the person requesting, that do you still want to wait? How does the system make this request? Remember, we do not have a connection between the server and the rider and the person requesting a ride. The person requesting a ride is the only one who can initiate a request. The server cannot initiate a record to the person requesting, to the requester. So how can the system ask the person requesting if they want to wait? And if they decide and say they do not want to wait, how does the system know to cancel that request? Remember,
okay, that's a very yes. I guess
the request that is still ongoing, right? Within this 1 minute, maybe at 30 seconds, a pop-up shows. I'm asking now how the pop-up works, right? Whether how the server would tell the person that the person clicks on no, how it's going to cancel that request, and cancel the whole thing on the server side, and then it shows the user the next viable option. How would this work?
Okay, in that particular scenario, I think the server does not really need to do that kind of a work there. The thing is that from the front end, that can be handled on the front end. Now, how is it going to happen on the front end? If this is the client here, it is the person requesting, you send a request here. So from the response back of this thing, the data, if it is successful, then on that particular scenario, we have a saved data there. Okay, this is the time that this particular request is being saved. So this has nothing to do with the server. That particular current time is being saved on the client itself, be it desktop app, mobile app, or on the web. It's being saved. Then timer begins to load. I don't know in so many programming languages, but I'm very sure in form of maybe a JavaScript. So it begins to count timing under the hood. Okay, the best example I can make of this is by using something like you are sending a maybe forget password for server to send you an OTP. So, and for every event that you send, you only have a period of maybe 5 minutes or 10 minutes to resend those things. Before you can be able to do that, the only thing that the server validates, it is the timing when you are sending. But the counting of everything is being handled by the client itself. So by using the client, it's so actually very easy. It is more of like a countdown. So set timeout can actually handle that if you are using JavaScript. So for any other programming language, I don't know the way you're going to do that. But
so you're saying the front end is going to cancel the already in-flight requests.
Okay, this is the way it works. You are not going to, it is not, it's still going to be the one. But now, when you receive response back that the request has been successful, then you begin to count. When you now begins to count, when you say at a particular time, okay, maybe after 30 seconds, a pop-up show up. When that pop-up actually shows up, that is when you now play, maybe count to, or maybe do something else. I use in the case of a forgetting password. Now, in the case of forgetting password, when you send that OTP, a timer begins to count. When that timer loads back to zero, a button is being shown to you. That button is for you to be able to resend. So the same thing happens here as well. So when that pop-up shows up, so cancel, you now send another request back. So the server actually have nothing to do. So everything is on the client side.
Hold on, you missed something, right? I know it might not be intentional. You mentioned that the client makes a request, requesting for a ride. Does the server return a response immediately?
Of course, it returns a response immediately.
What response does it return to the client?
Just a successful 200. That's all. Nothing more.
And then what's the server doing in the background?
Server, in the
Yes.
background. As of that particular time, what the server does is that it sends this thing back because okay, let's say the first request go, it fetch users and give to the client. So when you now send the second request to match, when you send the request to match a particular drivers, the server as of that particular point now send that event because there's already an existing connection between the servers and the rider. Send the server side event to the driver whether to accept or not. So it's just a one-time thing, and the connection is still open there. So the server does not actually does anything there.
Okay,
it does not do anything rather than sending an event to the driver.
Okay, what I'm saying is that the client now makes a request to the server saying, I need a ride. And the server says, okay, I will get you a ride. It returns a 200 response there, right? And then in the background, it now sends an event to the rider saying, are you willing to go on this ride? Isn't it? Yes. Is that what you're saying?
Yes.
And then if the rider now, if the rider says yes, what happens? Because right now, what happens if the rider says yes? Let's start from there.
Okay. So what happens is that right now, the rider has already accepted the request. So once the rider accepted the request, the thing is that it becomes matched. So that particular data is being saved on the database.
Yeah, but the client does not know that it has been matched because they don't have an existing connection to the server.
Okay, no. Once a rider accepted that, he sent a request back to the server. Once he sent the request back to the server responded back immediately to the to the client. And as of that particular point, there is a connection between the client requesting and the rider at the same time. So it's going to be a WebSocket connection that is actually immediate as of that particular time. So once the rider accepts, okay, bam, I accepted this order, then there's a connection between the client and the rider, the person requesting for the ride and the rider. So there's going to be a connection between the two of them.
Hold on first, we're skipping something. I'm talking about the process of matching. The client makes a request to the server saying, I need a ride. The server has done its work with the riders and has returned a list of 5 drivers saying that these are people you can match with. The client in return sends another request saying, I want to match with rider 1. Now, when he sends that request to the server, does the server return a response immediately and then reaches out to the rider in the background saying, do you want to match with this person? Or is it within that same request cycle, the server sends a request to the rider and says, this person wants to match, while keeping the client waiting? Is that what happens?
Okay, now, the second request that you're talking about is the matching request.
Yeah, the matching request, yes.
This is the client's back again. Now, if the client send another request again to the server, immediately, because for every request you send, you are going to get a response, whether you are not returning any data, but either the response is being successful or not, you are going to get that.
Okay, so the client makes a request to the server, and the server says, don't worry, I'll get back to you, right?
Now, when that thing happens, that second particular request is in a form of a WebSocket request.
Oh, so you are saying now that the client establishes a WebSocket connection with the server?
Yes, the second time, not the first one.
Oh, so it's at the second point that they establish a WebSocket connection with the server.
Exactly.
Right, that's
so now, what I'm trying to say the other time is that assuming that this thing is actually waiting, the client is actually really waiting for let's say by maybe the driver is actually busy for like 30 seconds before that time of 1 minute. Even without that WebSocket connection, what I'm trying to say is that once you send a normal HTTP request to the server, if the server responded back with normal,
could you label the server and the client and the writer and the client?
Okay,
just
thank you.
So we can know which one it is. Okay. All right, so that's the writer.
Yeah. What should I call? Okay, I will just call the client. Think of the first we understand.
Let's call it client.
So now, this is the second request now. The purpose of the second request is to match.
So establish this is a WebSocket connection between itself and the server. Okay.
And the server.
Okay.
Yes, now. So that is what happens there. But even without that, let's say this is a regular HTTP connection. When the server returns 200 back again, because you are the one that actually sent this thing. So the time is actually there. The time that request is being sent, you are going to save that locally. That is what triggers whether you are still waiting or not.
However,
even without the WebSocket connection.
If you send a request without a WebSocket connection, there is no way the client can know that the writer accepted that request or not.
Now, the only way is that when the writer now see a request, he saw a request. This is the request now. Now, it's now made for the driver, the writer, to accept this connection. And when that happens, they have the WebSocket connection together.
Yeah, but the writer does not know where the client is at the moment. The client has been communicating with the server. The writer has never communicated with the client before. So if the client makes an HTTP request to the server asking that I want to match with this person, the server returns a response saying maybe 200 processing or something like that. It has not matched the request. The server now sends an event to the writer saying someone wants to match with you, accept or not. Now, the writer decides to accept. There's no way the server can reach to the client and say connector. There's no way the writer can. There was socket connection in the first place. The writer can just reach out to the client it doesn't know about.
Okay, now let me explain this. How does the writer knows? Because this data, this request that we are talking about is being saved inside the database. Are we together? This thing is being saved inside the database. Now, in the case of, let's say, something like in a chatting application now, and this is a chatting application here. So when something is going to happen here, it's going to be called something like a conversation here. So this conversation can actually contain so many people together. So this is a client sending request. Here, the server goes there. This is a WebSocket connection where everybody can actually connect to. So once this man here can actually connect to this. So the request that the writer connected to comes with the clients. That is how the both of them have been matched together.
What I'm saying is there is no way the writer can reach out to the client if there was no WebSocket between the writer and the client in the first place, except the writer or the client has a connection to the server, an ongoing WebSocket connection to the server. There is no way they can communicate with one another. There has to be a form of communication with the other person. One person has to know the address of the other person, right? So if you send a request from the client to the server, and the server returns a 200 saying, I'm getting the writer's response for you. The writer definitely has to respond with something. You respond to the server, yes. The server has to return to the client. But apparently the server had already sent a response to the client. So that means there is no way of getting that response to the client except via a WebSocket connection. What do you think about that?
Okay, now I get what you are trying to say. Now, if you notice very from my statement, what I just mentioned earlier, it is the part that even though without the WebSocket connection, I made mention, and I mentioned that the second request is going to be a WebSocket connection to the server.
Yeah. I was saying, you mentioned that even without the WebSocket connection, it could still work, and I wanted to understand how that's.
Okay, now what I'm trying to say concerning that one is going to work. It is the aspect of actually telling the client whether to be able to cancel or to still wait.
Oh, I see.
So without that, normal HTTP request to serve that particular purpose.
Okay.
That is where I bring that without HTTP, without a WebSocket connection.
All right. Okay. So I think we've done a pretty extensive work right now. I'd like to give chance to others to ask questions. If you have a question, please could you raise your hand? So far, we've seen at least an example flow of how this should work. Although we didn't have time to deal with this at scale because, maintaining like 20,000 concurrent connections at peak for this kind of system. And it's something one should be concerned about. But yeah, do we have questions right now? Please raise your hand. Okay, I have one person raising up the hand. Godwin Lawal, do you want to go ahead, Godwin?
All right, thank you very much. Please pardon me if I have some questions that may sound weird. I'm just a beginner too, so please don't consider my question as why should I be asking such a mundane question? It's
Okay,
just that I'm just trying to learn.
Problem.
Just trying to.
Yeah, just go ahead and ask the question.
So okay, so okay, so okay, so this rider now, will it be is it a mobile application or will like this is it client side or server side, this rider?
Okay, this rider. Come again with your question.
Now you identify three entities: the client, the server, and the rider. This rider now, because obviously the client will be the user facing end. That would be server. That would be client side. The server will be that one self-explanatory. This rider, will it be a mobile application or will it be a server?
Let me explain the way the thing is here. I think this is the client that actually confusing. Now, what we mean by clients here was not actually maybe being client. It is the request. I don't know the English, so I'm not an English student, so I don't know how I'm going to call it. The person actually looking for a ride. Let me just call it customer. And this is a customer. So we have removed clients now. So anything client is that what they're actually interacting with. So a client might be on a web, if you are using websites, might be Chrome or any other thing, you get it. And the client also can also be mobile app. And if not mobile app, it can be a desktop application. Are we together now? So that is a client. So the server is actually different. So the reason why we just call this one client is that I don't know what to actually call, how to actually call it. So both of them, they are clients.
Okay. So for this request, if the customer is making a request, why are we making two requests?
Godwin, please could you take that question after? I'm taking only one question per person, right? So you can just raise your hand again and I'll take you next.
Okay.
Thank you.
Right.
Daniel Bello, please speak just one question, please. If you have another question, you have to raise your hand again. All right, go on.
Yeah, thank you, Adeji. So I wanted to confirm what sort of architecture this would be and how scaling would be considered, going forward, seeing that there might be lots of, users on that same platform, as well as how risk conditions would be handled in this situation. Thank you.
Okay, now, if you are going to handle something like a risk condition, because we are going to structure our database in the form where we are going to have something called transaction here. So every request that is going to come is going to follow a structure called first in, first out. Are we together? first in, first out. Because I don't see no point whereby a customer sending a request to the server, when you send a request to the server, it returns you with a riders. So part of those riders can also be returned to another customer. But where the problem lies is that when it actually accepts. So immediately it accepts, automatically an event should happen that this particular rider can no longer be available again immediately to the user. So it's going to be in a form of a queue that all of them will just line up, first come, first serve.
So can I go ahead? All right, one question, right?
Yeah, one question, please. To follow up on that, I would be skeptical about calling it a queue, right? Because if it's a queue, that means only one person can request a ride at any one point in time. It's a queue, first in, first out, right? First in, first out actually is a stack.
No. First in, first out is not a stack. That's a queue. First in is going to be the last to be out. That's a stacking stage.
Oh, sorry. Yeah. I would be skeptical about calling it a queue or a stack. I think he's asking about the architecture of this system. What would you call the architecture of this system?
As well as scaling. How would scaling be handled? Yeah,
exactly. How would you scale this system? Just briefly. If you don't have a link, it's fine.
Yeah. So regarding this system, the way it's going to work, since we already have Redis here, to the best of my knowledge, we already have Redis here. Maybe the underlying technology might not be so much help, but if you use actually a very fast technology, it should help. But that one does not maybe actually solve the problem. But since we have Redis, I think they actually go far, very, very far with that. So even though you are sending many requests, you are not actually eating the database directly. What serves you the request is already inside the memory at the same time. So it is much more serving a request at a more faster rate, more than any other request actually reaching the database. So to the best of my knowledge, that is what I understand.
Okay, all right. Thank you for that question. Just a tip, right? Redis is actually single-threaded, and I would be skeptical of still using Redis, a single Redis instance at scale. I would be looking at having a Redis cluster handle my request at scale to ensure that, when you use Redis in this case, still only process to one person at any one point in time. So yeah, my workforce.
Yeah, actually right.
But at scale, you want to use more instances of Redis.
Something actually came to my mind now. Actually, forget something came to my mind as you were talking. So in this particular kind of a scenario, I think I've actually used something much more, maybe not even Redis. I can use Redis for the caching part of it. Using something like that can maybe accept high throughput, like something like Apache Kafka. I think it will be better in that place more than using Redis.
I think Redis is still fine. If you introduce Kafka, you're introducing latency. And everybody will wait.
Yeah, that's a message broker. No, if you mention Kafka.
Yeah, you're introducing message broker, and then you're dealing with scale here, and people need to get response fast. Dealing with Kafka, you're introducing a whole lot of latency that shouldn't be there, right? Still have to deal with the consumer.
Yeah, so is Kafka not a message broker?
Yeah.
Yes, Kafka is a message broker.
Yeah, Kafka is a message broker. I don't think you want to use Kafka in this case. Yeah, someone is asking, Mubarak is asking, should the clients directly communicate with the rider? All communications are supposed to go through the server while the server handles the distribution of requests. So at some point, just to point out, at some point you mentioned that when the customer makes a request to server, WebSocket connection, by the way, to the server, and the server tells the rider, hey, would you like to go on this ride? And the rider says yes. Then the rider now establishes a direct WebSocket connection to the customer. At this point now, you have 3 concurrent WebSocket connections. You have customer to server, server to rider, rider to customer at this point. So he's asking that should the customer actually communicate directly with the rider,
Okay, in that particular case, once the customer and the clients actually connected together, I don't think there is no, because at that point of particular match, every other connection should be dropped. So just like normal chatting, I talk with the customer, the rider talk with me. So every other connection, apart from that, should be dropped.
Okay, right. Yeah, that's fine, but there should be a problem. There will be a problem here. What if the rider has a bad connection, bad network connection, or the customer's connection is really bad and gets broken somewhere along the line? It's gone. Everything is gone. The customer cannot communicate directly with that rider again. The rider cannot communicate with the customer again. They all have to reestablish another communication with the server. I think that might not scale so well. Mubarak, you want to put a voice to your question? Go ahead, please.
All right. Good evening. So I dropped that message on the chat because I have one major question I wanted to ask.
Okay.
I just raised my hand for the major question, but you can go ahead with I think Sarcastic is doing justification to the clarification. You can just go ahead. So when is my turn, I'll just ask the major question I want to ask.
Yeah, go ahead. Ask the major question you want to ask.
All right. Okay. So I've implemented a scenario like this between a buyer and a seller, right? Whereby you want to confirm if the buyer and the seller are meeting, whereby the buyer is going to like trigger a request to confirm that, okay, yes, I'm meeting with the seller. So during the implementation, initially we're using I want to get clarification between server-side events and the socket events, socket IO. So initially we're using SSE events. I created a service to handle the SSE requests, but the limitation I had with the SSE events was that it's too fast, in the sense that in milliseconds you could get maybe like up to four emission back to the mobile app within milliseconds. So in that case now, let's say I want to navigate the user to understand that, okay, yes, these guys are missing already. So it's going from my end now, it's going to trigger the navigation like up to 3-4 times because it's so very fast, so very quick. So that case now, I do not know if it is the backend developer that didn't handle it properly, or maybe that's how the server side events is. So when I compared to the backend developer, he said I think he couldn't fix it, so he had to change it back to socket IO. So now my question now is that in this case now, I had the issue when I was implementing from my end. So in this case now, why are you choosing to use SSE and not socket IO? Like, what's the advantage of using SSE in place of socket IO, or what's basically the difference basically?
Okay, now sending a particular HTTP request to a server is actually maybe one way. It's actually one direction to send this thing here. So at that particular point, establishing the rider and the server already have an established connection before, and that connection is for the purpose of their location. Are you getting it?
Yes.
Now, so sending a request to the server notify the rider. Now, the reason why I choose this SSA, I don't want to introduce another WebSocket this thing, but still here the server can actually use that WebSocket connection to send that particular request, the notification to the rider. But server-side event is actually one time something. It's just something like maybe you make a payment online. Maybe you are actually integrating a payment gateway. Now you already send this thing, so they are about to send the request back to you to confirm that, okay, this thing is actually confirmed. For that particular purpose, you don't really need the WebSocket connection that you just pay forever. Whenever that is happening, let server just notify the rider. So instead of using an open connection, so they serve actually different purposes. So in a form of something that has to do with the notification, server-side events will be best using that particular aspect than open just a bi-directional communication. You communicate. So I think it should be better that if it's just a one-time something rather than using open connection that can be able to talk anytime.
All right, but in place of the rider here now, the customer now, once the customer makes a request to the server that, okay, yes, I want to book a ride, I want to pick a ride, yeah, and then the rider receives the request. So in that, when the customer has already triggered the request, the customer is also should also be listening to a response back from the rider at that point. If you are booking a ride from Bolt now, and then you chose the rider. So it takes you to a step by waiting for the rider to respond back to you, right? So that WebSocket connection can't still be maintained. It's not
now
SSA entirely.
Now, what I mentioned earlier is that the request that actually fires actually two requests. The first one is to get the list of the drivers. The second one is actually a WebSocket connection. Are you getting it now? So the second one is actually a WebSocket connection. So whatever communication the server is going to send is just going to send it through that WebSocket connection. So the first one actually normal HTTP request that actually goes and fetch nearby drivers. So after getting the one, then on matching, that's another request. So that's supposed to be a WebSocket connection to the server.
All right. Thank you very much for the clarification. Thank you.
All right. Thank you for asking that question. Do we have any questions from? Okay, I see something here. Someone is talking about latency when using a message broker. Actually, the purpose of a message broker is an asynchronous communication, right? Where latency to a certain extent can be tolerated. In this case, latency that is introduced by using a message broker might not be able to be tolerated in this case because you would need several consumers running at any one point in time to ensure that request is as fast as possible. It's not something you can really use in this case. Stephen, you want to ask a question here? Can you go ahead?
Yeah. Good evening, everyone. So, Sakai, I don't know, you mentioned you were not sure about using a queue type of logic, a queuing system, and I'm not sure about using a Redis. Well, I'm not sure you went ahead to mention why you might not opt in for those two options or those two systems.
Right. I was talking about a question was asked about the architecture, and he said the architecture is called first in, first out. And I was trying to clarify that when you're defining the architecture here, you can't necessarily use the word a queue. You can't call the entire system a queue. The entire system is not a queue, right? That's what I mean by I would not call it a queue. I mean we cannot queue customer request and server request. I think we did not get to talk about scale. That's a place where we could really deal with scale, where if we want to limit our system to about 10,000 users, we can decide and say we queue requests. We do some kind of priority queue here, where first in, first serve. We can only handle 10,000 users right now, but if it becomes 10,001, we simply queue the next person's request until we have space to accommodate the person making the request. So that's one thing that can be done.
Okay. Yeah. So I think the queuing system was brought up in case of concurrent write request. So when people are trying to open a write request open a write request for one single rider, how does the system handle that kind of condition?
Okay, Father, please go ahead.
Okay, now that is actually where I said that the queue is going to be implemented. When you send the first request and you are already being sent a list of riders, you send the second request to match with a particular driver. Let's say like two people send a request at the same time. So part of the rider that is being returned to the first customer is also being returned to the second customer as well. So since the second request is a form like a WebSocket connection, so immediately a driver access, since you already have a connection with the server, immediately the server immediately send the request back to that other customer. Then the list of the, the list of the riders here will be dropped. The one that is not actually available will be dropped immediately.
All right. Thank you. Okay, we have one last question. This is the last question I'm taking.
Yeah, thank you to both of you.
Yeah, it says when you say server-side event, are you referring to something similar to sending a Firebase push notification to the driver application?
Okay, yeah, that is what I mean.
Oh, okay. All right. So it's something similar to that. Server-side events, you can describe it as something similar to that, but it's not really that way. I mean, as Profile is saying, something similar to that, but it's not really the same thing. Case of server-side sent event, yeah, you send event from the server like that, but in the case of push notifications, they're different.
Now, the thing is that if you are sending the request is going to contain some data, not actually maybe notify you of any other distance. So it's containing a kind of a data that's been sent with it. Just like it is more of like it is not maybe the client sending request to the server, but the server doing the same thing that clients normally does.
Yeah. Right. With that, thank you very much. I asked for. Okay, I have two people raising their hands for questions. I've not heard from Aziz. Aziz, can you go ahead?
Okay, good evening, everyone. So I would like to get clarity on server-side events. So what does it actually mean? Is it something like is it sending WebSocket requests between servers and clients? Is that it?
Okay. A server-side event does not necessarily mean a WebSocket connection. Now, when before an event can happen, normal in an application, we only have whatever the kind of operation that you are going to perform. It does not more than a crude operation. Either you create data, you are reading data, you are updating, and you are deleting. Now, before an event can really happen on the server side, out of those 4 operations, theory must happen. It's either you are creating something, or you are updating, or you are deleting. So when that things happen, the servers already have all the clients. He knows the clients very well. He knows all the clients very well. So when you send the request to the server now sends another request. Normally, the client has sent request to the server, but in this case, it's the server that is sending request back to the client. So the request contains some data as well together with it, not just ordinary, maybe normal notification. So it is either at the point of something is being created, updated, or deleted. So in our case now, what actually happens here is a creation of something. And what actually created is request. It's writing request that is being created. So on that particular point, we just listed for that particular event. Okay, whenever a customer requested, like, let me use a Laravel for example now like this now. In every of our model, there is a static method here called bootable. And inside that bootable, you can be able to list all the events that can happen. Maybe paraventure, you are developing an application like okay, a user can actually have a profile in his own, maybe in this thing. So when you are creating a user, you wanted the profile to be created. So you just listening for that event. Okay, on creation, do this particular thing. On updating, do this particular thing. And on deleting, perform this particular action.
Okay, so who listens to that server? Okay, from what you explained just now, so it basically means that the server is the one that actually triggers that event. But who listens to that event? And how is it actually done?
Okay. The client here listening to the event that is being sent from the server.
Okay. Yeah. How is it done?
Okay, now let's say, for example, if you are using, let me say, using sarcastic mention of something that it won't actually link it together because it is more like something that is quite different in a form of notification, like what this thing does, FCM does. So the writer already has built-in listener there. So anytime a request is coming, it's always ready to listen for that particular event. So whenever it comes, you just pick it up there. So they are supposed to be a listener from the riders. So whenever the event comes, you listen to the event, it fires.
Okay.
All right, allow me to chip in here, right? So the thing about server-side event is, in the case of server-side events, the client is not making a request. The server is the only one that can make a request. It's a one-way thing. First of all, the client in this case now could be anything. The client initiates a connection to the server, right? In JavaScript, usually with event source, right? You initiate a connection to the server, and the server now holds that connection, keeps it there, and then can respond multiple times with multiple events, right? Or with several messages. The client cannot send a message. Only the server sends a message. Only the server sends anything. The client cannot do anything. And that's why it makes sense here to actually use a socket connection, socket IO connection, or WebSocket, rather than server-side events, because the server-side events, the clients cannot actually do anything, meaning the rider cannot do anything to the server, can only send a separate HTTP request or something. It makes sense instead in this system, as we have already concluded, to use a socket IO connection or WebSocket connection between the server and the and both clients in that case. Does that answer your question?
Okay. Yeah. Thanks.
All right. Thank you very much. Do we have any more questions? Please, I will take these two questions and we'll end. Steven, please go ahead.
Do I have my answer? No, the second person can go.
Lord, thank you. Godwin, please go ahead. Godwin Lawler.
All right, thank you very much. So they've actually had two questions, but the first one has partially been answered on how to implement a listener for the events, for the server-side event on the client side. But since you said in this case, it will be much more efficient for us to use WebSockets, so that one is more. I think that's fine. The question that I want to ask now is, you made mention of a cluster of Redis would be much more efficient than using Kafka, because that one will bring more complexities to the system and latency and all. But I was expecting something. I was also expecting you to mention something like RabbitMQ. But if RabbitMQ is not something that can be used, is there a relationship between these three, RabbitMQ, Kafka, and Redis, or when do we use which?
Okay. Well, Father, do you want to answer the question, or do you want me to talk about it?
Okay, I've not really have experience using Kafka, even RabbitMQ, but I know that RabbitMQ and Redis can be used in the form of a queue when you actually queuing a data. So there's a form of something that Redis actually perform more for like a Kafka and RabbitMQ. When you actually have something like a publisher and a consumer, So that is why I can still mention about something like that. This thing, I latency in this thing. So the three of them really actually have similarities, but they serve a different purpose in different kind of a scenario. So actually broadcasting maybe many events at the same time. So Kafka have higher throughput, can handle much higher throughputs more than any other, whether RabbitMQ or Redis. And the thing with Redis is that if a server crashes at the same time, your data may be lost. I think maybe that is the reason why Sarcastic may mention that it's better to even use clusters of Redis. They are not actually maybe a single instance of Redis. So to the best of my knowledge, this is what I can explain regarding that.
Oh, okay. Yeah, let me add my 2 cents to that. So the thing about when I mentioned Redis cluster, I'm not talking about it being efficient to use Redis cluster compared to using a single instance of Redis. I'm talking about when we scale, right? When you scale and begin to handle way more requests than you would usually handle before. There's a possibility that a single Redis instance might not be able to handle this request. Why? Because Redis is single threaded, right? And this means that it can only handle one request at any one point in time. Single threaded, yeah, could be asynchronous, but it can only handle one request at any one point in time. If you want to handle multiple concurrent requests, you want to scale to a Redis cluster. The relationship between RabbitMQ, Kafka, and Redis. All right, let me first answer the question, why not use Kafka? First of all, Kafka is not for this use case. The latency for Kafka is much higher because you do not only have to send a request to Kafka, because Kafka still has to process that request and send it to consumers. The latency is higher, like even way higher than a simple HTTP request, if you are doing averagely the same thing. So Kafka is not really built for this use case. Kafka is for streaming. By streaming, I'm not talking about like streaming real-time kind of stuff like this. It's not really for real-time kind of stuff. It's for handling, say you want to handle bulk processes, you want to handle asynchronous communication where you don't need your response immediately. Kafka is the best case for that. Yeah, of course, you could run a Kafka instance, send a message, produce a message from a producer, and you get the message at the consumer side immediately. But that's because you are just testing locally. When you get to production, you're dealing with producing like 50 messages a second. Trust me, Kafka cannot handle that case. Neither can RabbitMQ. They are just message brokers, right? The relationship between both of them and Redis is that Redis happens to act as a layer to handle fast state caching and all of that, which RabbitMQ does not provide at that point in time. RabbitMQ just simply handles your connection, but if you want to add a layer of, you want to add handle state, you want to handle caching, you want to handle rate limiting, RabbitMQ does not give you that capability out of the box. If you're using that also with Socket.io, if you really want to scale horizontally, and then you want to support, message coordination, broadcast, and you're broadcasting to multiple rooms at the same time. These are things you don't get with Socket.io or WebSocket out of the box. That's where Redis comes in. With Kafka, you do not need Redis because Kafka has its own database already in it, so you don't need Redis for anything. In the case of Kafka, does that answer your question?
Yeah, yes, it does. Thank you.
Right, thank you very much. Yeah, by the way, Mubarak, the issue you had with server-side event is from the back-end side of things. They have to fix the bug on their own side. With that said, we've come to the end of this session. Thank you so much for taking this session, Profile. Thank you so much. We've all learned a lot on server-side events and WebSockets and overall on system architecture with building a ride-hailing system, and this is really beautiful. We have also beautiful questions from people. One last thing I'd like to mention is that you can follow me on X at my account here on Sarcastic, and I'd like you also at the end of the session to subscribe to DevMeets X account and the YouTube channel. You can also watch the recording on the YouTube channel after the session. I'm recording it here, but I'm also streaming live directly to YouTube, so you can also see it there. That's it. Thank you very much. Again, I'll see you next week with another session on system design. We'll be having another developer design something else for us. They do not know what we'll be designing up until that time. So those who have here, have a nice day. It was the well, and then I'll see you next week. Bye.
Bye-bye.